Sure. Who is
There's a. You have one?
Oh, yeah.
there's a second. We can also organize
I
is it
An
okay.
analog laser pointer. Yeah.
So again, cordial welcome to our today's speaker, Professor Howard Stone from Princeton University, who is very, very famous, one of the leaders in his field. I'll tell you right away a little bit about his research. Howard has received his undergraduate training at University of California in Davis, followed by a PhD at Caltech and postdoctoral training at University of Cambridge in England. Yeah. He's been professor at Harvard for 20 years before he moved to Princeton in 2009. And his research focuses on fluid dynamics, especially at the interface between engineering, physics, biology, and chemistry. And there I have to stop because he doesn't allow me to tell you more. So please, Howard.
Okay, thank you. So, first I want to say thank you for the invitation. I've had a really wonderful day, and I got to talk not only to the faculty, but students, and it was very interesting for me. So, I've tried to craft a talk that hopefully will be interesting for a physics audience. I called it Flows of Complex Fluids because some of the work I do overlaps some of the work in the soft matter area here, and I've included at least one problem that appears to have a bifurcation in it, and another problem that breaks symmetry, and actually there are a couple people in the audience that contributed to that I'll tell you about as we go. So obviously we all have our research groups to thank, and I'm certainly no exception to that, and so I've been fortunate to work with a really wonderful group of people over the years. So I'm going to do this. I'm going to start with a few slides that I call a fascination with fluid mechanics. It's just to try to convince any skeptics in the audience that there can be interesting problems in out-of-equilibrium systems that involve fluid motion. And then I'm going to tell you about what looks to be, maybe you'd call it almost an engineering problem. It's a T-shape, and I'm going to show you that something gets trapped in there, and the motions are so-called laminar flows, but they're what are called a modest Reynolds number. So I do a lot of work at low Reynolds numbers. People in the soft matter community here mostly work on small systems. This is a flow where the Reynolds number is in between 100 and 1,000. It's relatively fast. You might think, well, I don't know. You'll tell me what you think. Okay. And I claim to have discovered something in this very classical field that hadn't been recognized for hundreds of years. So, the next problem I'm going to work on, it was worked on actually by Matan, who was a graduate student with Paul, and Naomi Oppenheimer, who's sitting back, and one of my postdocs, involves the interaction between an elastic material and a fluid. Those are called fluid structure interaction problems, and I'm going to tell the story via symmetry break. So that's going to be the next part of it. And then if there's time at the end, I'm going to tell you about how you might observe patterns in an ordinary café latte and how that ties to a fluid mechanics problem. Okay, so why should fluid mechanics be interesting? I don't know. You go to dinner, you like wine, you observe the so-called legs in a glass of wine, these very regular structures, and you might ask, where do they come from? And they're a fluid mechanical phenomena that, if you were interested, come from something called a surface tension gradient along the surface. The alcohol is a mixture of water, and the wine is a mixture of alcohol and water. The alcohol evaporates, so you smell that. That means any liquid on the side of the glass when you swirl it is primarily water, which has a higher surface tension than the water-alcohol mixture at the bottom, and that creates an upflow. If there's too much liquid at the top, gravity wants it to be down, and you get a beautiful instability that's known by the name of a Marangoni instability. Of course, Marangoni was an obscure Italian physicist of the late 19th century. The problem was actually first described by James Thomson. You don't know him, but you know his older brother. You know his younger brother, Lord Kelvin. And then you're supposed to say, well, if Lord Kelvin's last name was Thomson, where do you get the name Kelvin from? But that's another story. Anyway, so that's a fluid mechanics problem. Legs in a glass of wine. There's something called the hydraulic jump in fluid mechanics. It's normally taught in civil engineering classes, but the kitchen version of it is a high-speed jet of water comes down, spreads out along the bottom. At a finite radius, the jet the liquid jumps up to a finite height, which you can observe, and that's called the hydraulic jump. And you might be interested in what is the radius of the jet as a function of the flow rate of water. It turns out that's a very hard problem to analyze if you try to analyze problems. It's an old classical problem, and we got interested because of microfabrication is what would happen to the hydraulic jump if you have a substrate that has a very fine texture to it, a little like the carpet. So this is a slide of a similar experiment of a jet of water. This patch that you can see has in it a microfabricated pattern. The pattern is at the scale of tens to hundreds of microns for every length scale, the spacing, the height, the diameter of the posts. I should say the experiment I'm going to show you, the pattern is hexagonal, not square. That's a detail. If you're not confident in what 100 microns is, those of you fortunate enough to have your hair, the diameter of the human hair is 100 microns. And if you look here, you can't see the texture. It's a very fine texture, and so visually you can't pick it up. If you do the hydraulic jump experiment with a hexagonal pattern, then as you increase the flow rate, you see a pattern, and the macroscopic pattern picks up something about the friction, if you like, the hydrodynamic resistance of the pattern. In a fluid mechanical terms, you'd say the fluid has memory. That's because in this case it has inertia, and it's picked up something about the asymmetry or the friction associated with the pattern. So we look, yeah.
Why does it happen to be hexagonal?
So it's hexagonal, I kind of hinted at it. The pattern, it turns out, that's here is a hexagonal pattern of posts. It's not a square pattern. And then it turns out, if you, at least the way we tried to rationalize it, if you think about any of these patterns, then the direction you go, the kind of friction you'd see per unit length depends on the number of posts per unit length, and that depends on the details of the pattern. So
Are those posts all over
they're all over this patch.
the circular patch?
And the fact that you see it still outside the pattern means the fluid has some memory. It's water. Water has no molecular memory, but in this case, the system adopts the memory because the fluid has inertia, and so it knows something about the past that it's flowed over.
Have you tried this with a quasi-crystal pattern?
No. Could think about it, I suppose. Anyways. Okay, good try. Okay. All right. Just to point out other things that we looked at, just to kind of point out that they're puzzles that I think are interesting. This is an experiment we did a few years ago. You're looking through a microscope at a substrate that has on it bacteria. Each of the bacteria is rod-shaped and about 1 micron. And I should say, in interest of full disclosure, if there was no motion in the liquid, each of these bacteria would be undergoing kind of random movements on the substrate. That's a known phenomena in some bacterial systems that the biophysicist calls twitching motility. In the presence of flow, we do experiments where we were interested in how flow changes a system. The flow goes from top to bottom, and any reasonable person would say the flow creates a stress. The stress acts on objects on the surface, and the things should move. And in this experiment, you can ask yourself which direction the objects move. And they're going which way?
Up.
Yeah, so this was an observation that we kind of stumbled on, that when you take a natural system, in this case a bacterial system that has a form of surface motility, in the presence of flow, you generate an upstream migration that we've studied a little about, somewhat unusual. Okay. And then finally, I think I have 2 more pictures. If you like these kind of living systems, this is a living system. It's a bug. The bug lives at an interface between water and air, and this is a curved interface. It's what you refer to as a meniscus. This bug, you can see it has no arms or legs, so you might ask, how does it move itself? I know the Soft Matter Center, you know a lot about surfaces and surface tension, so this bug, when it wants to move, arches its back. By arching its back, it deforms a surface, creates a curvature of the interface, and a surface tension-driven flow carries the object along. You can decide for yourself whether you find remedy. No, you're not right. No, you look like a friend of mine. No, you got me worried for a second. Okay. Okay, and finally, I'll just close with this one. This is a shorebird. It lives in relatively shallow water. It does not like getting its head wet. When it wants to feed, it starts to spin in circles. There are a number of people that have studied how it feeds, how it uses its beak to collect water. Anyone know why it's spinning in circles when it wants to feed? By spinning in circles, it creates a rotating flow. The rotating flow near an interface creates an upflow. So this is a way the shorebird creates an upflow and brings organic matter or shrimp or things it wants to eat to the surface. I should say that at an APS meeting with about 1,000 people present, one of my former graduate students, who's a professor at a distinguished university, showed this movie for some reason. I can't remember. At the end of the talk, there were no questions. That sort of upset me, so I stood up and I asked, does this mean the shorebird knows more about fluid mechanics than we do? And he said in front of 1,000 people, I can't speak for everyone in the room, but I can assure you the shorebird knows more about fluid mechanics than my PhD advisor. So that was kind of just a quick survey of kind of things in fluid mechanics, individual snapshots of fluid systems. You can decide whether you find them interesting, and some of them have stories behind them. So I'm going to start with a problem in fluid mechanics that I'll tell you exactly how I stumbled on it. It sort of has a puzzle in it. The puzzle is kind of an everyday kind of flow. I'm going to try and convince you of that. And we've sorted out part of the puzzle, and I'll tell you that now. Okay, so the flow involves a pipe, effectively a piping element. The flow involves an intermediate value of the Reynolds number. Just to keep clear, most of the soft matter people, I think, study the case where the Reynolds number is much less than 1. Turbulence is a flow where the Reynolds number is much greater than 1. This is an intermediate value, everything I'll show you. And we're going to study T-shapes. Now, T-shapes are important in engineering systems because you need to deliver fluid to different places. In the lab, this is your T-shape. And inside all of us, we have blood, sweat, air. We have lots of T-shapes inside living systems. Actually, someone showed me today, Reynolds showed me today that there's an image from Leonardo da Vinci of flow in a T-shape. So what I'm telling you about has been known to people for hundreds of years. I'm going to now show you something that hadn't been noted before, either in simulation or experiment. And I'm going to suggest where it might be important. Okay, so everything we're going to do is one geometry, though, that the flow comes in at the top of the T and out effectively symmetrically at the sides. The kind of experiment we do looks a little like this. We take a system. It's sometimes a millimeter scale system and sometimes a microfluidic system. We have inflow, and we try and make the system as symmetrical as we can, and we have outflow. And so I could just ask, the definition of the Reynolds number is a viscosity of the fluid, the density of the fluid, the mean speed, and the geometric length. And so you're allowed to ask, what does the flow look like? And I think most educated people would say, well, must look something a little like that. Flow comes in and flow leaves. And if this were the case, I just want to go through one argument. If this were the case and you put objects in the flow, maybe they're red blood cells. In my case, they're going to be rigid particles. Maybe they're going to be bubbles. You might think if particles come in on a streamline, then if you follow the streamlines, all the objects you would claim should leave. If they come in at the top, they should leave at the sides, at least according to a picture like this. Everyone sort of agree with that? Okay, anyway, so, and if you were nonlinear dynamical systems person, you'd say it's an unstable stagnation point. Everything goes away from it eventually. Okay, so we were originally working on this because of some people at the plasma physics lab that were interested in building a system to have clean water, and they were interested in what happens if there were contaminants, and so they wanted us to study this. And so this is just an image of what happens when you have a high Reynolds number flow of water, and we were trying to calculate and understand the impact of particles on the wall to know if there was going to be damage to the wall. And one day, air got stuck in the system, and so this is the same image, except the black dots are air bubbles. I'll just say at the outset, gravity does not matter. So it doesn't matter what orientation you do this experiment in, that when you turn on the flow, and you ask, what happens to the bubbles that enter the system? You observe that objects are accumulating in the middle of the system. So this is the observation. If you don't find it interesting, then you're allowed to.
Are they?
goes on.
So I see objects coming from the top to the bottom, passing apparently through the line. Are they in a different plane?
Yeah. So what I'm going to kind of show you is you can sort of see here. You see two lines of bubbles. I'll tell you why that is. And if you've ever talked to physicists or people who study turbulence, you'll know that the way people see certain structures in turbulence is you add bubbles to it, because bubbles go to the center of rapidly rotating flow. And that's sort of happening here. The puzzle, though, is the objects aren't leaving, they're getting trapped. And the question is, why is that?
Howard,
Yeah.
is gravity relevant? Which way is gravity?
Yeah, as I said, in this experiment, for this probably experiment, gravity was into the page, but this observation is independent of the orientation of the channel relative to gravity. It turns out, yes, they're bubbles, so it turns out what matters is a density difference, but not a buoyancy force. Okay, so this is the observation that I now want to suggest has in it a solution to the Navier-Stokes equations, this brand solution of fluid mechanics, that was not noted before by anyone studying this problem. And I should say, by the way, for those of you that do simulations, there's a huge literature on simulations for this geometry for practical reasons about engineering, physiology, and everyone, and I could try to answer why, I think because of the way they asked the question, completely missed something interesting that I'll now show you, or try to show you. Okay, so it doesn't matter what the angle is. Now, this is a slightly different angle. It's not a 90-degree bend, it's a 100-degree bend. If the flow is slow enough, in this case the Reynolds number less than some value, all the bubbles that enter leave. If you notice when they come in, they're actually leaving spinning. I'll tell you why that is. That's a natural feature of any curved pipe. All of you are sitting with your elbows bent. Your blood flow is such that the flow in your blood vessels is Reynolds numbers comparable to this. The flow is similar to here. On the other hand, if you do nothing else but double the flow speed, which means double the Reynolds number, you trap bubbles. So these two images, I'm going to say, tell you that there's a bifurcation in the system. The flow qualitatively changes in the so-called laminar flow state when all you've done is double the speed in a very modest range of Reynolds numbers.
But this requires bubbles. If you used other particles, it would.
Yeah, so what I'm going to say, this is an experiment with bubbles.
Right.
It turns out if you do any experiment with an object less dense than the fluid, you will see this.
Right. But so if you don't have the tracer particles, the flow field is different. So the tracer particles are helping create the flow field.
I can't answer that definitively. The way I'm going to try and answer this question is I'm going to show you a single-phase flow simulation that rationalizes why this happens, and the simulation has no objects in it other than a single-phase fluid. And then I will show you an experiment that has all the features of the simulation. So I don't believe anything I'm telling you has the bubbles playing a significant role in the flow. A fluid mechanics person would say, you know, are the bubbles feeding back on the flow? I don't believe that's so important. I'll give you evidence for that. But, you know, eventually it probably does when you get a high enough bubble concentration, but it's not the first order effect. Okay, anyway, so this happened accidentally in the lab, and we spent some time trying to understand it, and it's here where we realized that there were things taking place in a very ordinary system that no one had quantified before. And I don't have an analytical theory. I could just show you how we understand it. Oh, but I don't feel bad about that. The Navier-Stokes equations are nonlinear. They're nonlinear coupled PDEs. I don't believe there are almost any nonlinear theories for the intermediate range of Reynolds numbers that people study. So. Okay, so this picture, it's sort of right and it's sort of completely wrong. Okay? And the reason it's completely wrong is because this is a three-dimensional geometry. And because it's a three-dimensional geometry, I'm going to tell you about a very classical flow problem that in the fluid mechanics world is called Dean flow, because about 90 years ago, Dean studied flow in a gentle bend, just a curved pipe. Now, that's what I'm saying. If if you're interested in what happens in your elbow, then this is what's taking place. And I should say, because of the creativity of mathematicians, physicists, and engineers, almost everyone has studied a flow with a constant radius of curvature, even though most systems have abrupt changes of curvature. Doesn't make a large difference, but it does make some qualitative changes. And what you find is that in a pressure-driven flow in a pipe, the flow is a parabolic, and the solid curves here are effectively showing contours of constant velocity of a nearly parabolic flow with a maximum velocity in the middle and zero velocity in the walls. And when the flow goes around a bend, if you compare the inside of the pipe to the outside of the pipe, the dashed lines tell you what is the so-called secondary flow. So when a flow goes around a bend and the Reynolds number is high, the fluid is doing this. Okay. It's traveling as if it's a parabolic flow, but it picks up two vortices, which are sort of the lines you saw. And so it does this as it goes around a bend with curvature. Okay, now it turns out that's going to be sort of important in the story I'm about to tell you. And so Mark's question about why do you see bubbles in a line is this background or so-called secondary flow has swirl. The fluid mechanism would say axial vorticity. And so bubbles want to go to the center of that when you add them to a flow that has enough curvature. Okay, so if you ask why this video, why do you get bubbles going into lines, is because anytime you go around a bend, the fluid is creating two vortices for you. It's tied to the speed of the flow and the degree of
The two vortices are in the plane that we're looking at, or perpendicular to the plane?
perpendicular to the plane.
Sorry, so maybe this is just something everyone knows, but stuff only accumulates in the center of a vortex if it's less dense than the fluid.
Yeah.
And so that's why you can only see this with bubbles.
Well, I'm not sure everyone knows.
No, I'm asking. I
just
didn't know that. I was that, but
just making a statement of sort of physics that if you take a rock on a string and you swirl it, there's a centrifugal force that wants to go out. So if you reverse the density difference, it goes to the center. So in a flow, any flow that has local regions of so-called vorticity or local rigid body motion, then objects that are less dense will tend to go to the center of that, and objects that are more dense will go away from that. Okay. But the mystery then is not so much that you get them going to the center, but why do they get trapped? What's holding them there? And the first hint is, so we did numerical simulations, so this just shows streamlines of a flow as you increase the Reynolds number. I should say the first grant I tried to write on this, and I've given up on this problem, by the way, because after 4 years of writing grants, all getting turned down, I've stopped because can't get supported. But 1 year they said, it's your numerical code. Your numerical code is wrong, so please redo it. So we've done it with numerical codes in 3 different countries, and we always get this kind of answer. So the streamlines get increasingly complicated as you increase the Reynolds number. Yellow is what a mathematical person would color as regions of high vorticity over and above the parabolic state. And the region of the swirl, the region of vorticity, gets increasingly longer. But the fascinating feature is that above a critical Reynolds number, above a critical flow speed, when you look inside the flow, there's a critical Reynolds number above which the flow topologically changes. And by that I mean, in the fluid mechanics world, there's a term called vortex breakdown. Vortex breakdown is the observation that if you take a flow in a pipe and you spin the pipe very, very fast, then above a critical spin speed, there's a state where the flow, although trying to be aligned, has a pocket of fluid that just sits swirling inside the flow and doesn't go anywhere. And it's only been seen really in two laboratory experiments and one real flow. The laboratory experiment is a pipe flow that's rapidly spinning pipe, and then the aerodynamic situation is a very high speed flow where a vertical column of air comes off the aircraft. It's spinning very, very fast, and then there's an abrupt change where it blows up, and that's called vortex breakdown. And if you know Phil Holmes, who's a nonlinear dynamics person at Princeton, he had previously made a little mathematical model that said if you have a flow with a little bit of swirl, the vortex breakdown bubble would be a closed pocket of fluid inside the system, which has a recirculation opposite the main flow direction. So there's kind of a little mathematical guidance for what this might look like. And my claim now is that this is happening inside every T-junction when the Reynolds number is high enough, inside you, inside pipes, whatever. And the numerical evidence would be above a critical Reynolds number, most of the streamlines come in, swirl, and leave. There's a set of streamlines that are swirling and going outward, and they hit a stagnation point, and then they go backwards inside the flow. And it's the presence, it's the creation inside the flow of a place that has zero velocity. That's the topological change that occurs here that no one had noted before. And you can look inside this numerically, and you're allowed to be skeptical, is this what's going on? But my claim now is, and then I'll show you a couple more experiments, is that above a critical Reynolds number, there's a bifurcation. The flow creates a stagnation point. It creates an internal pocket of fluid that can't go anywhere. It effectively just recirculates. Bubbles, which are less dense, or any object that are less dense, gets pushed in, and then they just get stuck inside this domain. And the evidence for this is this experiment that we got lucky to catch. The flow is coming in at the top, out at the sides. This should be the most unstable point if you were to believe my first picture. In fact, it's the most stable point. And if you look at the bubbles, most of them are spitting outward, and then along the column of the center, you see some of them coming back. And so this video shows this trapped pocket of fluid just sitting there. To give you some evidence that this is a plausible explanation, you can do experiments with lots of different angles of pipe. For different angles, you can keep track of the Reynolds number and identify those places where you capture bubbles. The lower boundary of data points is what we measure in the lab, and the red, the colored curve here is what comes out of a single-phase numerical simulation for when you first identify this stagnation, so-called stagnation point, or the vortex breakdown phenomena. Anyway, so that's my evidence. And then the evidence that this is really quite generic and will happen even with fluid without tracer particles. So Mark's question, I'll skip this, is this video which has dirty water in it. You ask how long does it take to clean out dirty water. Above, at low speeds, you'd say a length divided by a velocity. Above a critical Reynolds number where you trigger this vortex breakdown bubble, then all the water cleans out except for the place where you have these trapped pockets of fluid which are created by the flow above a critical speed. Anyway, so that's my little story about flows in a very common geometry that hadn't really been first noticed before, and then of course since no one noticed it, no one really studied it except for simulation. Okay, that's my first story. Okay.
And if you look at perpendicular, you see each of them doubled.
Yes, well, in principle, that's what we claim we'd see. So in this case, that's what you should see. As soon as you have bubbles, you have this issue of the bubble feeding back on the flow. So only in some of our movies do we see two lines. Other times we just see one structure.
But in this movie, you would.
Yeah, although this is the only image we have of it, for whatever reason, that's all we took. Yeah.
Do you still have these two vortices if you increase the heights of the teachers?
Yeah, no, great question. But as soon as so everything I've shown you really is for a square. As soon as you have a rectangular section, then it'd be like flow in your elbow. The structure that sets the scale of the flow is the smallest dimension, and along the wider dimension, you then would replicate it. So if you had this kind of geometry with a sheet coming down and then branching into a rectangular section, you would get a whole series of these vortices. Every time the flow tries to turn the corner, it has to swirl, and it's going to swirl scaled by the confining height, if that's what you're asking. That the rectangular geometry will generally produce multiple versions of this.
With in the two channels that are perpendicular, right? I mean, I was thinking of increasing the heights like this.
So I have a flow coming in. Which way?
No, the flow is going like this.
Oh, so now, okay, the flow is going.
The flow goes like this and like this, right? But you increase the height of the whole.
Yeah, but because what I'm saying is because the flow is coming in and the flow has to turn.
Right.
Every time it has to turn, it's forced to produce a vortex, and it has to produce equal and opposite ones, and then those will get reproduced along the height.
Okay. Yeah.
Is it down how different it will be? It's not like Z2 structure, but there's rotation is symmetric.
You mean like a pipe coming into two discs?
Right, yeah, a pipe coming out like to plate, and so it can go in any direction, not just to two directions, but
Yeah,
It can go
so
here.
we haven't done that.
Mhm.
I have to be careful now how I say this. I believe I know what the answer is, which is that every time you come in and turn, you have to produce these vertical structures. And above a critical Reynolds number, I'm sure you're going to get some structure like this. I'll just say it's been studied experimentally by a set of groups interested in mixing, and it's been studied numerically. But to my surprise, no one asked the question the way you did, so they didn't really analyze the three-dimensional flow. They only looked in planes. And so there are a set of papers out that sort of describe this, but I think they missed the most interesting three-dimensional features. So there are a few papers out there, but they haven't really analyzed it with any care, as far as I can tell. Yeah?
So in all of these cases, there's actually 4 vortices. There's always 2 counter-rotating on either side of the junction?
Yeah, I mean, if you want to count that way, yeah, exactly. It would, here's one picture, but yeah.
Yeah, because from the bubble videos, it's not so obvious that there's 2, right?
Well, that's because at some point they start to get connected very, very near the plane of symmetry. So that's the level of detail I have. I mean, the closest thing might be if you looked at this image. Right, so whether or not you want to call this one, and there's one behind it, and then one and another behind it, they don't quite connect it. That's effectively the level of detail I have with this. So.
That's fair. I'm wondering if at the middle it looks more like the picture we were originally imagining.
You mean this picture?
Yeah, in between.
What I'm saying is wrong with this picture, although it's what every professor would probably draw without knowing anything, is it fails to recognize three-dimensionality, and without three-dimensionality you can't explain anything that you observe in the lab. And you can't make a prediction for that you might get this topological change when you get an internal stagnation point. Yes. That would be my suggestion. But I think it's a rational picture otherwise. It just sort of misses a lot of information. Okay. All right. So there's a second story I have, which is I like fluid mechanics and I've been trying to learn elasticity, so we've made up a couple problems that have both. And I'm going to tell this story through symmetry and symmetry breaking. And if you have detailed questions, Naomi and Matan are sitting in the audience. So if you have the Navier-Stokes equations, the inertia terms are on your left and the viscous terms are on your right. And in place of a pressure gradient in a viscous term, it's common to write the divergence of a second order tensor, the stress tensor. And low Reynolds numbers means you neglect this term. And therefore, you're asked to solve for a divergence-free field, an incompressible flow with u as the velocity vector, and the stresses are divergence-free as well. And what I'm about to tell you has many links to other areas of classical physics. I'm just going to show you one version of it that at least some theorists aren't aware of, so I thought you might find this interesting. As soon as the Reynolds number is low, there's a symmetry of the flow, which effectively says that if you have a geometric symmetry, the flow has the same kind of symmetry. So these pictures, it's very hard to tell whether the flow is going left to right or right to left because of the symmetry of the linear equations and the symmetry of the geometry. And it really doesn't matter what these shapes look like as long as they're left-right symmetric. On the other hand, and someone mentioned this to me today too, maybe it was also late, there's something in the literature called the Tesla valve, which is thought to be a valve good for mixing flows, but it has implicit in it the idea of a high Reynolds number flow, a very fast flow. And if you take this geometry and you make the Reynolds number low, you can't tell whether the flow is going left to right or right to left. It has the same streamlines. For a linear boundary value problem in the fluid mechanical sense, if you reverse the forcing, which in this case is reversing the pressure gradient, you just reverse the streamlines. And so the geometry is sort of irrelevant.
Those two pictures are different, though.
Slightly different, but effectively, if you follow the streamlines, they're effectively the same.
I mean, unless it's a different device, there's like a bump on the left bottom part that's not.
Yeah, but this is a, well, I don't know what that is. Patrick Tablin, who sent me these pictures, said these are the same device, effectively, and he did one experiment left to right and right to left, and they're more or less the same. And the Reynolds number, is always finite, but it's small. Okay, now the famous movie of this made in the 60s by G.I. Taylor tries to make this point that reversing the direction or reversing the forcing reverses the flow, and some of you probably teach with this, that you take fluid, you put it in a device, you make it go one direction for several times. That's putting the forcing in one direction. Now you ask, what happens when you reverse the direction? You know, will you continue to mix the fluid? And in this case, when you undo the motion, which in this case is reversing the direction of the stresses, or the thing that drives the flow, in this case you just undo the flow field. And so you, other than molecular diffusion, you undo the streamlines, and so everything comes back the way it started. So some of you, when you study small scale motions, you might teach with this video. Okay, and the way this comes out in the active matter world, what's called the active matter world about swimming, is you could ask, how would you swim if all you do is you take a, whatever the thing at the back of your boat is and wave it back and forth, but when you wave something back and forth and the Reynolds number is low, each half cycle undoes the other half cycle and you don't go anywhere. And the way you get around that, the way you break that symmetry, is you use a rotational motion that's continually increasing in angle. So G.I. Taylor constructed an object that was rubber band driven with two opposite helices, and that swims. And that swimming is analogous to what bacteria do. So E. coli has a rigid, effectively a rigid hook at its back, and it's capable of swimming by continually rotating the helix at the back. And bacteria are, in some sense, the prototypical active matter that generated a lot of interest in the field. So this you would call how you break the symmetry of the simple stroke. And the person who did the most to kind of highlight this in the physics community was Ed Purcell, who, after winning the Nobel Prize in physics, got very interested in swimming microorganisms. And he created a puzzle for you that I'm going to show you on the next slide. So Ed Purcell wrote this beautiful article called Life at Low Reynolds Numbers, where he tells some of these stories and comments on the video of G.I. Taylor. And Purcell made the following remark, that if you have a single hinge, and apologies to those of you in the audience who know this, but I'm assuming many people don't. Purcell made this remark that if you had a single hinge and you just open and close it, then you're stuck with the so-called reversibility paradox, or the reversing the direction of stress. So a single hinge can't swim. So he made an example. He said, well, what about, and he called it the scallop theorem, although he remarks that, a scallop is really a high Reynolds number swimmer, but ignoring that detail, it has the geometry of his single hinge. So he made up a so-called two-hinge swimmer. He said, suppose you take this diagram, and in the reference frame of the object, you move the left-hand angle down, so you end up with a shape you call shape 2. And now in the frame of this object, you move the right-hand hinge down, so you end up with shape 3, which of course is a symmetry of reflection symmetric to shape 1. And then you take shape 3, and you move the left-hand arm up. And then finally you go in a full circle, and you take the right-hand arm and you move it up. And so you've done a circuit in angle space, except now you have two angles. And he just remarks that this will swim. He doesn't tell you which direction. He doesn't tell you how fast. He just says, in general, this will swim. This gave rise eventually, although about 15 years later, to, in the physics community, a set of papers from Frank Wilczek and others who tried to use the structure of the low Reynolds number flow problem to argue on geometric grounds how might you talk about swimming. And I don't have enough math to talk about that, so I'm going to tell a slightly different story. But this is one way you get around symmetry in this case, is you don't have one angle, you have two angles, and that's sufficient in the geometry of the shape space to allow swimming. In fact, there's even a paper in general relativity, for those of you who want to read this, that has exactly the same words and applied this principle to what they called swimming in space-time. I don't know enough physics to do that, but they translated the Wilczek picture, which was translating the Purcell picture, to breaking of symmetry in the systems. Okay, so the problem I'm going to talk about is a little different, but
Were you the first one to do that problem the right way?
Well, so my group was the first group, I believe, a long time ago that tried to just answer this question
Yeah,
by calculation.
yeah.
Yeah. So, yeah, but that wasn't relevant to the story, so I didn't say that.
Okay.
So, okay. Okay, so the problem I want to tell you about is a rigid plane. You can think about this as some part of Paul Chaikin's experiment where he was doing sedimentation. You take a sphere near a plane and you let it fall due to gravity. And you ask, what's the velocity of the sphere? What's the trajectory the sphere will fall under? The experiments use fluids that are a little more viscous than water, and as I said, Naomi Oppenheimer and Bhargav Ralabandi were two theorists working with me who worked on it, and then Matan, who happens to be Naomi's husband, said, I'll help you with the experiment. I don't know, you guys can tell me what the story was. Anyway, so this is the story. So this problem has a very simple symmetry, which is that if gravity is down, then the sphere can only fall down when the Reynolds number is low, so it will translate keeping the same separation distance from the wall. It can rotate, but it can only translate vertically. And there's a symmetry argument that you can construct for yourself to prove that when the Reynolds number is low. It cannot drift relative to the wall. So we're going to look at the problem when there's a flexible sheet. And then I'm going to tell you a theory story this time. So the experiment looks like this. You drop a, where is it? You drop a sphere near a plane. The plane is flexible as the particle falls. You can look at it relative to this white line, and it clearly drifts away from the sheet. And a set of still images showing here. So a flexible sheet coupling to elasticity, which is sort of like a polymer, breaks the symmetry of the flow, and it then allows a drift. Okay, so if you're a theory person, here's the calculation. Please calculate this for me and tell me how does the drift velocity vary as you change the viscosity and change the sheet properties and change the size of the sphere. And I'll tell you what most people would do if they wanted to calculate this problem. They would numerically calculate it by coupling the deformation of the sheet to the fluid flow, and you just calculate everything. So I'm going to show you a different way to calculate it that requires to a first approximation, no calculation other than knowing about the flow of a single sphere. And it's a theoretical idea that comes up in many different areas of applied physics, whether it's E&M, fluid mechanics, or elasticity. And in fluid mechanics, it's referred to as the reciprocal theorem. And it's a way you can attempt to do this calculation only knowing known facts that are available to you without ever constructing the velocity field or the pressure field, but what you do calculate is the drift velocity. Okay, I'll try and tell this story because maybe you'll find it interesting. I'm going to skip that. Okay, so the idea of reciprocity has a long history in physics and math. It goes back at least to the study of acoustics. In acoustics, as first kind of written about with Lord Rayleigh, it doesn't matter where the source and receiver are, you can always reverse them, and the signal is the same going from, if you reverse the role of the source and receiver. And so this is kind of the first time you learn about this, often in a math class, where you study the differential equations for acoustics, which are effectively the Laplace problem, and you call it Green's theorem. It turns out in aerodynamics, this was an idea like this, and a different set of problems was noted in the 50s. And in the fluid mechanics world, it was popularized in the 1960s and 1970s, but it was first noted by the great Henrik Lorentz that there was a mathematical structure of the problem that allowed you to get information. And in fluid mechanics, this is called the Lorentz reciprocal theorem. It's the same Lorentz you're thinking about. Okay, now, of course, the first idea of this in elasticity is often quoted a year before in an elasticity problem, Dubetti. So in elasticity, the idea I'm going to tell you about is called Betti reciprocity. But most of the historians claim that Maxwell beat them all to it in a slightly different context, and they refer to an earlier paper by Maxwell for this whole idea of reciprocity. And in fluid mechanics, there was the late Professor Howard Brenner at MIT, and because of this thing I'm going to tell you about, which makes it seem almost mysterious, he would talk about this as getting something for nothing. And I'm going to try and tell you what that means in this context. It's how do you calculate something almost without calculating anything. Okay. All right. So here's the idea, and this is first outlined by Lorentz more than 100 years ago. And there are E&M analogs of this. So you have a problem you want to solve. The top line is a problem you want to solve, a velocity field, a stress field. This is going to be the flow with an elastic sheet. The problem below it is the same problem, but you only change boundary conditions. So what I'm going to tell you about is, you look up in a book for the motion of a sphere near a solid vertical plane. I can look that up in a book. Because of these two identities, you use Green's theorem, and there's an integral relation between these two problems where S is all the boundaries. And what it relates is the velocity field in, say, a model problem and the stress field in a problem you want to solve. And it's a scalar identity that relates two different problems. And, if you haven't seen, if you know this, well, whatever. Okay, so it turns out the integral of the stresses, which is this language, n is the unit normal on the surface. The integral of the stresses are forces. In this problem, the force is down. It's a force on a sphere. So I don't have a physical intuition for this. This is really sort of a kinematical structure, or maybe there are probably some other ways to describe it in the sense of variations. But this is an identity. And what I'm not going to show you is how you take this identity and answer the question quantitatively, what's the drift velocity of a sphere near a wall? And the argument goes like this. You want to answer this question, and of course your intuition is to do numerics, but here's how you do it. You take this identity and you say to yourself, the model problem I want to do is a sphere moving normal to a wall, and that's a rigid body motion. So the u in a model problem can come outside the integral. And what's left over is the integral of stress, which is a force, in the problem you want to solve, and that's down. So one force is down, the model problem is perpendicular to it, that inner product is 0. And all that's left over then is an integral over the surface of this other quantity. And the surfaces are a plane and a sphere. Okay, and there's one thing I'm going to leave out, which is that you make them the same by doing a Taylor series of the deformed shape about a plane. So this is an identity. It's a scalar identity. And on the sphere, you know something about the velocities. And on the wall, you know something about the stresses, because you have a problem that involves bending. And so you just start counting. You say, rigid body motion of a sphere. Known force on a sphere. I looked that up in a book. The stress in a model problem is a pressure, but the pressure is tied to the shape of a sheet, and I look up in Landau-Lifshitz mechanics problem how the forces cause bending of a sheet. And the u is the velocity on a wall that comes from doing a little Taylor series. And from all this, it turns out you can solve the sheet problem in Fourier space, and the integral you need to do is an integral in Fourier space, and the drift velocity comes from this integral. And all of these pieces you just put together sort of analytically using known information in the problem. Now I should say Naomi and Bargov sort of figured this out, and Naomi's probably upset at the way I described it. But that's roughly how you get from an integral identity in the classical literature an analytical solution to this problem. And if you compare what the drift velocity is as a function of lots of the geometric parameters, the size of the sphere, the gravitational constant, the density difference, the bending modulus, the viscosity of the fluid, the data points are all different experiments, and the solid curve is essentially analysis, and the parameter that matters involves the bending modulus of the sheet, which is the elasticity, and the tension in the sheet, which is set by holding the sheet vertical in gravity. And the calculation itself didn't come out of something, a complicated numerical thing. It came from this analytical trick that, to a first approximation, all theorists have forgotten. Okay, so that was my second short story, and I'm sort of running out of time, but I have one more short story I want to share with you. Possible? Is that okay? Sure. I'm not sure I'm doing very well here. I'm getting a lot of angry looks in the audience. Okay, so the last problem involves patterns in a cup of coffee, and I'll tell you where this came from. I first want to start with two slides, one involving oceanography and the other involving David Greer. So. In oceanography, there's a phenomenon called double diffusive convection, which says that when you look in the ocean, which has salt water, and you have a cold object, which is colder than the ocean, what you often see are patterns, kind of horizontal patterns that are traces of fluid flow that is sketched here, where you put an ice in a water bath that has a density gradient created by salt. So this is an experiment you can find in the literature. Again, this experiment is a column of ice, so that's trying to cool the fluid. And in the bath of water is dense fluid at the bottom, like a lot of salt in water, and less dense fluid at the top. And when you try and create that static situation, it's unstable, and the system creates a pattern, and that pattern is a set of horizontal fluid cells. And it's called double diffusive convection, because you have two diffusing quantities, in this case in the ocean, salt and heat.
Is it radially symmetric around?
This could be a 2D problem or radially symmetric. I'll show you a radially symmetric version. Okay, now, I'm not an expert on it, but the thing, other than the misspelling on the slide, in this problem there's a horizontal gradient of temperature and a vertical gradient of density. It doesn't have, they can be in the same direction. In this problem they happen to be perpendicular. Now, 20 years ago, David answered a puzzle that people had observed, which was that when you take an emulsion of low-density droplets, which eventually start to rise to the top, that's called creaming in the emulsion literature. And David, you can correct me if I'm wrong, but this is what I understood. Over time, even though the tube is only about 1 centimeter in diameter and maybe 30 centimeters high, over time you start to see patterns occurring in the system, and the patterns were convecting cells. And David pointed out that in this problem what happens is small temperature differences in the lab, temperature differences across the cell, are sufficient to drive this horizontal convecting pattern. This is an example, unrecognized at the time, until David explained it, of what you'd call double diffusive convection. The experiment I'm going to tell you about is you pour coffee into a cup of milk. And so it goes something like this. You take a hot milk, you put it on the counter, and you pour in coffee. And it turns out if you pour fast enough and wait, what you'll observe is the appearance of a set of horizontal strata that are best kind of shown by the image on the right. You observe these patterns. And I should say, unlike almost every experiment in the literature which are carefully controlled, there's nothing carefully controlled about this. It's just, you take the glass, you put it on the counter, you pour in the coffee. And so it took us a while to realize that this experiment has all the elements of what's called double diffusive convection, even though there's very little control. And so it's this pattern I just want to briefly tell you about. And I should say, of course, I didn't think about it. This came by email from somebody. He sent me an email. He said he's asked lots of people. He sent us a picture. I had no idea about it, so I gave it to a graduate student who was looking for a project for a semester. It turns out this person never answered my emails back when I wrote him that we had understood something about it, but the New York Times found him and interviewed him. So, okay, so here's the little story about this, and why you don't need much control to do this. So the normal double diffusive problem, which goes back 80 years, is the observation that if you have a density gradient, it means you have a vertical density change with position. And if you have a cold boundary and a hot boundary, a horizontal temperature gradient, the fluid can't be in equilibrium, and the fluid adopts a cellular flow pattern because it's trying to kind of equilibrate the change in density that's associated with the change in temperature, associated with whatever change in temperature also occurs vertically through the existing background temperature gradient. This was first kind of recognized in the oceanography literature, and it's normally done in a very controlled setting. And as David also pointed out, you get these kind of funny horizontal convecting cells as soon as you have these features. Now, obviously, milk is not a good thing to work with, so we're going to work with water and salt. You use salt to create density in a system, and you pour in fresh water. You pour it in at a certain rate, and the needle always has a certain size. And unlike most experiments, the system starts uniform. It's a completely uniform container of hot water. the thing we've discovered was that the pouring, by creating a very complicated pattern, creates a density gradient for you. And if you create sufficient density gradient, you get a hydrodynamic instability. And so it looks like this. In the saltwater experiment, it looks just like the milk experiment. If you pour it in above a certain speed, you get these systematic layers. And you can use the intensity of light to back out what the density difference is. And the movies look the same. And I should say there's nothing really special, but there's something somewhat dramatic, is if you try to stir this occasionally, as long as you don't stir it too much, and if you stop stirring, it just recreates this pattern, because this pattern exists for tens of minutes, because it's being set by the slow cooling of the container to the ambient environment. And so it just has this feature that, as I'll show you on the next slide, it's the pouring that starts to create a density gradient, and the density gradient is responsible for driving a hydrodynamic instability. And this movie will eventually end up at the line patterns on the left. And so I'll just close with a couple things, that what we then discovered was that if you pour slowly, you don't see any distinct patterns. But if you pour fast enough, then you start to see these stripes appearing above a critical speed. And you can see it in the two movies I have. And so kind of our new observation in this problem was that the injection process is sufficient to create density changes enough to drive a hydrodynamic instability in a system that's slowly cooling. What you don't see here is the temperature. And they're slow movies, but the one at the top is just below a critical threshold of speed. Of course, that means there's a dimensionless parameter I could try and tell you about. And the one on the right is above a critical threshold of speed. They look more or less the same at this scale, but if you give the bottom one time, it'll form these stripe-like structures, but the upper one won't. We've done numerical simulations of all of this, so we've done experiments where we track particle motion. We've done numerical simulations where we try to calculate everything with parameters we mentioned, and to a first approximation, they show similar structures, that they show horizontal strata as in the same as the ones I showed you in David Greer's thing, and from numerics you can try and back out some of the more quantitative features. Okay, I realize I've used all my time, so I'll just stop with that and just tell you, I've told you a few stories. I kind of just briefly did the what you call layers in a café latte. I told you a little about this fluid structure interaction problem through the lens of symmetry, but I tried to also show you there's a theoretical construct that many people aren't aware of that's kind of cool. And then I started with this bubble trapping problem, which is, well, sort of different, but it has puzzles that we don't completely understand. And with that, I'll stop.
Questions?
I have a quick one, which is once you've done the simulations, do you have any theoretical prediction for what the relationship between the lengths of these layers is?
Yeah, so
or what sets the scale in the first place?
Yeah.
Like, is it something easy to understand?
So in all instability problems where there's kind of a temperature difference, there's what you call a critical Rayleigh number. There's a critical driving force above which, if the temperature difference is large enough, you get an instability. So in this kind of problem, it's known that there's a critical Rayleigh number. What's a little unclear is what is the length scale that sets everything, but the length scale that sets everything is controlled by the density gradient, which you call d rho dz. So the z in the denominator sets a length scale. So 1 over rho d rho dz, the inverse of that is gives you a length scale. And so that length scale is helping control the scale at which this happens. But you have to be above a critical temperature difference, if you like, or a critical Rayleigh number to trigger it. And so in this literature, there's someone's calculated what estimated the critical Rayleigh number, and our experiments are about there, and the scale is set by the density gradient that most experimentalists set by preparing their experiment. And in ours, it's created kind of in this haphazard by pouring.
Then? Can you like measure your
so
lengths and get back out what
Yeah, so
that
we use
gradient
dye.
was?
We use the dye color to back out the density gradient and then test it.
Okay. Cool.
Sure.
Back to your bubble trapping question. What happens if I increase Reynolds number further, would I create more of these places?
Above, there was one little slide I have. I have a little one slide that shows you sort of the idea. It's right here. It's right at the beginning. Sorry, bad. Here. So, for for a T junction at low Reynolds numbers, the flow is kind of laminar. There's nothing interesting about it. The flow swirl. You can't trap. Above a critical Reynolds number, I claim there's a bifurcation where you get this so-called internal stagnation point and vortex breakdown you can trap. When the Reynolds number gets too high, the flow is naturally unsteady, and then everything is getting thrown out
So
of it.
everything explodes into
Yeah.
turbulence.
Yeah.
There is no second bifurcation.
Not that we've seen, but we've really only studied, Reynolds numbers at the order of a few hundred to 1,000. So it has this feature that there's a window where you get trapped. Oh.
Does the latte thing survive tilting the cup?
Haven't done it, but
Because normally there's things like the boycott effect and stuff, which screw up the flow near the surface.
yeah,
if
but the
you're
boycott
sitting-
effect is driven typically by
Basically.
dense objects that want to sediment, and
Right.
so that it has this feature. Paul's pointing out there's a very famous thing that if you want to design something that sediments, most people would just take a container and they let things sediment. And this guy Boycott just noticed that if you make a small change in angle, then the particles don't have to quite fall as far before they hit a wall, and that cleans the fluid above them, and you get a natural circulation.
Which is macroscopic,
Yeah.
the whole thing. So
But
I'm
I
wondering
think
whether-
we haven't done that, but I think here you would just, you still have a vertical, I think you'd still have basically
Right,
a
but you
vertical
wanna have-
temperature gradient.
You
and
want to have one big swirl instead of your opposite eddies that you're getting inside, right?
Well, okay, I should say, I don't know the answer, and the best thing when you don't know is to say, I don't know, so I don't know. Maybe we could
I
talk
can just
about-
go to a coffee place and do it.
Yeah, although someone pointed out that we don't make coffee the way they do in New York. In New York, they put the coffee in first, they said, and they pour milk in after, so. That's what someone joked to
You
us.
can't change that.
One of
You
my,
could
one of,
you could
yeah.
also do a trick where you impose the gradient.
Yeah, but we
Right?
wanted to, we stumbled on this different problem.
Right.
Everyone has imposed a gradient. We were
Okay.
trying to, we kind of noted here, you can use the flow to generate a gradient. It's somewhat complicated, but you can generate all these patterns without the control.
Any more questions? If not, let's thank Howard again.